Hello, everyone, and thanks for joining us today. My name is Kelly Quinn Sands, and I'm from NASA Glenn Research Center, and I'll be your moderator for this webinar on Aviary, NASA's new digital modeling tool for aeronautical engineers to innovate new aircraft designs. As part of my role at NASA Technology Transfer, I work with NASA scientists who have developed new software that may have applications outside of the aerospace industry. NASA software is a free resource and is available through NASA's software catalog, which I'll show you a little later. Aviary is the result of collaborative efforts from NASA's Glenn Research Center, Ames Research Center, and Langley Research Center. Our presenter today is Jason Kirk from NASA Langley Research Center. Jason is a researcher at NASA Langley's Aeronautics Systems Analysis branch. He has a bachelor's degree from Purdue University and a master's from Georgia Tech in aerospace engineering and has been at NASA for 6 years. His research interests include systems level analysis of environmentally sustainable air transports, including electrification and alternate fuels, as well as creating the tools and methods needed to model those aircraft. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation, so if you have any questions, please type them into the chat and we will answer them during the Q&A session at the end. And at this point, I'm going to turn it over to Jason.
Thanks for that intro. So as you now know, my name is Jason Kirk, and I am the lead for Aviary. Let me know if those slides are showing up correctly.
Looks good.
All right, yeah, so I'm the lead at Aviary here at Langley, but I also want to call out my co-leads. We have members at Ames and Glenn as well. And Aviary is a tool that is jointly funded by T-Cubed, EPFD, and AATT. So with that out of the way, let's get started. So some of the main topics that I want to cover during this presentation is, of course, what is Aviary? Why do we need Aviary? And how is Aviary transformational? So breaking that down into a couple subtopics, which is an overview of what the code is, the challenges that it's intended to solve, a little overview and a deeper dive into using the tool itself, and some examples from projects that have successfully used Aviary. So at a high level overview, Aviary is a tool that was designed to meet a challenge. And I'll be hitting on all of these bullets in a lot more detail during this presentation. So to just quickly skim through, there is a limitation from our existing tools to model aircraft designs that makes it more difficult for us to analyze the truly advanced concepts, things like the X-66 or electrified propulsion aircraft. And we would like to be able to more easily model those aircraft. So Aviary is designed to meet those needs, chiefly maintaining the capabilities of all the tools we already have, building upon that to support electrified vehicles and electrification, easily integrate external models if you have a tool that does a very specific discipline analysis, including that in the design process, using state-of-the-art analysis and optimization techniques. We have a focus on gradient-based optimization, and we'll be open source releasing, or we have open source released, to maximize collaboration with our partners. So with that very high-level overview, I want to dig down a little bit deeper into what challenges exist that facilitated the need for Aviary in the first place. So we're going to start at the very highest level of design. So Aviary is targeting conceptual design, which is the phase at the beginning of a product lifecycle where a lot of key decisions have to be made. There's not a lot of information, not a lot of funds to spend, not a lot of time to spend, but the decisions that we make, as you can see in the chart above, there's very little actual funds spent, but the decisions made lock in a lot of the costs for a project. And this doesn't just have to be project costs. This can also be things like the potential performance of an aircraft. The decisions that you make very early in the design phase will be very hard to change later. For example, if you are looking at the TGPW, you can't suddenly reverse course and start looking at a blended wing body halfway through the project. So you've already locked in the potential performance of that aircraft very early on. And for NASA Aeronautics specifically, there are some questions such as, what vehicle configurations are worth pursuing, what technologies buy their way onto a vehicle. Do they buy their way onto a specific configuration like the TTBW, but don't make sense for something else like a distributed electric propulsion aircraft? And then once you've made some of those decisions, being able to have an estimate of the projected performance and cost of that aircraft. And conceptual design is an inherently iterative process. So your time and resources are limited. So you got to do as much as you can with that. You want to be able to do a large quantity of analysis, which allows you to explore more of the design space, try out more configurations, more combinations of technologies, and see what makes sense and what doesn't. And you also want quality of analysis, or maybe better put, fidelity of analysis. And that helps drive down risk. You have less uncertainty in the performance of your aircraft if you've been able to do some more rigorous analysis of it. But like I mentioned before, time is limited, so we can't always do that. And this is especially challenging for aircraft because we have so many competing disciplines that all want something different from the aircraft. And typically we'll have discipline experts that might be familiar with one or two, or maybe even a superstar who's familiar with three, but no one is generally an expert on every part of the aircraft. So it requires a lot of collaboration and compromise between designers and experts, and this takes time. And for complex aircraft, this is made even more difficult because those discipline experts can't design their subsystems in isolation. Everything they do has a radical impact on everyone else. So these images represent a portfolio of different technologies that ARMD might be interested in. We have electrified propulsion, boundary layer ingestion, thermal analysis and thermal systems, acoustics, and all of those have impacts on different systems. You'll have couplings between aerodynamics and structures, coupling between acoustics and aerodynamics, or propulsion and thermal, and really understanding and being able to quantify those complex interactions is necessary to be able to figure out what an advanced concept is actually going to look like if we were to build it. Now, traditionally, the way this historically was done is each discipline team would be isolated in terms of data. They'd hunker down, they'd crank out analysis for propulsion system, for example, get a result, throw it over the wall at an aerodynamics team. They take those results, they rerun their analysis, they make some new trades, they make some new decisions, but then they have to pass those new results over to the propulsion team again so they can rerun their analysis. It's a manual iteration and it's slow. We can't truly do rapid iteration like this. And what that means is we might run out of time before we can really nail down what those interactions do to the aircraft design. We miss that, and we come up with a suboptimal design that's basically treating the aircraft like the sum of all of its parts. It can't be more than the sum of those parts, and it also might be less than the sum of those parts, but we don't know it. So it's suboptimal. The new modern way to do this is advanced digital design. We're smashing through that wall, and we're directly hooking up all of the discipline team's analysis tools through software so that the tools can actually talk to each other. And this means that there's no wall. All of the teams are working on the same aircraft level model that in and of itself contains all of the different individual disciplines. And by having those tools linked up, we're designing the aircraft holistically. This also opens up some neat new tricks, like we can use version control on the models so we can have a history of how the aircraft design is evolving through time. We're removing that manual iteration so we can both move faster. And then with that extra time, we can invest in bringing higher fidelity tools earlier in the design process to bring down that uncertainty. And what Aviary does is it's that software that stitches everything together. It's why we weren't able to do this effectively before, but now we can, and we are enabling this new design workflow through Aviary. So now that you have a little bit more context on why Aviary exists, I want to kind of circle back and hit some of those key points of what Aviary does. So Aviary's goals are, we want to take all of the capabilities we already had with our existing and legacy tools and preserve those. We don't want to lose any of that. But then we want to build upon that to use a modern code architecture. We're using Python so that it's easy for users to go into the source code, make modifications, and modularize the analysis. So if you need to bring in that higher fidelity tool, you can swap out what already exists in Aviary out of the box and put in your custom tool or method, or supplement a method that exists in Aviary with a couple extra pieces of analysis. So in that way, Aviary is both a standalone aircraft design tool, but also can become a framework when you start using those advanced capabilities. And this is enabled through some packages, Python packages written by Glenn, which is chiefly OpenMDAO and Dymos. And those are very, very powerful tools that allow us to do that modularization, as well as bring in some state-of-the-art optimization techniques for both the aircraft model and for mission analysis and trajectory optimization. And that really makes, it's the beating heart of Aviary, what makes a lot of this work. And doing that, we can provide the capability to analyze future advanced aircraft concepts, including electrification. A lot of the models needed to do at least a very computationally cheap low fidelity analysis of those types of aircraft are included with the core distribution of Aviary. And as I keep hammering home, we are an open source release. That's very important to our project because that maximizes our impact to the aerospace research community. And it also makes Aviary a better tool because we've already gotten a lot of fantastic feedback from external partners that we may not have been able to get as easily or as quickly if Aviary was difficult to share. And a little quick brief history on Aviary. I mentioned some of the legacy tools. I want to explain that a little bit. Throughout the different aero centers, we have some different aircraft design tools that we typically used. At Langley, it was a tool called FLOPS, and at Glenn and Ames, it was a tool called GASP. And both of those are written in Fortran, and they've been around for anywhere from 30, 40 years. They've been updated along the way. But Fortran isn't the easiest coding language to learn and then make changes to a complex source code. So independently, both centers started working on a translation of those tools into Python, and we both had similar ideas of how we wanted to modularize it and bring in some advanced optimizations with packages like OpenMDAO and Dymos. And as soon as we realized that we had similar goals and we were working on a common vision, we decided that we should collaborate and team up. And instead of working on separate siloed projects, we combine those two tools into one, call it Aviary. And then once we have that, we can build upon it to really expand and push the state of the art beyond just preserving our legacy tools with a couple nice quality of life modern conveniences. So that's really where the birth of Aviary started. And I kind of want to more explicitly state what makes Aviary special and how it is transformative. You can kind of think of transformation as having two bins or two categories. There's revolutionary. Is this technology or project state of the art and advancing that state of the art in and of itself? So Aviary does that through better capturing of coupling with subsystems that the user can bring in your own tools, modernizing our legacy tools. But there's also an important part of transformation that's a little more external. Is it inspiring innovation elsewhere? Is it affecting other projects and other people outside of your team? And Aviary, we work very hard on that second category. It's very important to us. So open source, again, is a key way to enable that, make sure that the more people can get their hands on this code, the better it's going to be. And also, the more we're advancing the state of the art across the industry. Aviary is also early career led. Myself and my co-leads, we're all considered early career here at NASA. We're the next generation of engineers building the next generation of advanced design tools. And we also put a lot of effort into outreach and tech transfer. It's something that is very important to us. So we're always trying to get out there and sell the virtues of our code and show people what they can do with it. And we do that through things like documentation, examples, video tutorials. We put a lot of effort into that level of polish for the code. We want it to be as easy to use as possible, something that you can give, for example, to a student who's just starting out their engineering degree and get them to start playing around with aircraft design and learning about that new design process right off the bat. So next, I want to talk a little bit more about actually using Aviary. What does it look like inside? How does it work? What makes it tick? And what it looks like to use it. And I'm going to start by going into a lot more detail about the modularization of the code, because that's a really core piece of it. It can be not just a tool, but also a framework. So what this chart is showing is this is kind of a visual representation of how does information flow through an Aviary model. You have a lot of different pieces of analysis. Each of these individual blocks would be an individual discipline that's been discretized into an independent piece of analysis. And those pieces of analysis might have parts that run before you need to do mission trajectory. This would be your sizing section. You have mission optimization and solving that trajectory. There's your traditional aircraft design loop where you're converging on a design. And then afterward, there might be other things you want to do, some post-processing. And all of the components here that are in blue are things that Aviary can support out of the box, or at least has a method that you can use to do that type of analysis. And everything in green is either something that a user can bring forth and add to Aviary, and it's not limited to the examples shown here, or it's something that they can substitute out an existing module. For example, if you want to do cycle design, you can pull out Aviary's built-in propulsion, which is just reading a performance table, and you can slot in MPSS or PyCycle and do full-on cycle design. Likewise, if you want to add on a completely new subsystem that Aviary doesn't out of the box have any analysis for, like cost modeling or acoustics, you can do that, throw that in there, and design your aircraft around those metrics. And by having everything modularized like this, it actually makes the optimization very powerful, because you have a lot more freedom of choice over how you set up that optimization. You can choose any objective function, any design variables, any constraints, including variables that you have added to the model through adding your subsystems. So what I mean by that is, if you add in a cost model, you can now optimize the entire aircraft to minimize cost. If you also add in an acoustics model, you can add a constraint that there are certain flight conditions where noise on the ground has to be below a certain point, while also minimizing cost. And then if you have your cycle design that you added in earlier, you can use those as the design variables. So now you're designing a propulsion system cycle to minimize cost while obeying acoustic constraints. And this is extremely powerful and makes the conceptual design phase a lot more dynamic. You can do a lot more unique and interesting trade studies, and it's very easy to do so in Aviary. So how do you set up a complex optimization problem in Aviary? How do you build this large and complex model? And Aviary has a user interface that we like to call layered. It has different levels of complexity, and you can start extremely simple, or you can dig way down in the source code, break it up however you like, use bits and pieces, make your own custom Python script. So there's this whole spectrum. So at the most basic level, you can interact with Aviary with just a text-based input file. No programming, you don't need to know Python, you don't need to know anything. You just have to have a text-based input file. You run command line, and Aviary handles the rest from there. It will move on to the level 2 layer and define all the subsystems and mission analysis that's needed to run that basic input file. And then it will build up and go through all the complicated Python coding needed to actually set up all of these little blocks of analyses, connect them up properly, and then actually execute the analysis. But you can jump in at any level. You might need to use some of the more complex features of Aviary, and you need to use maybe the level 2 interface, where you need a little bit more flexibility in defining some things. A single line command line can't capture everything you want to do. So you can use that, and then you only need a little bit of Python experience and some knowledge of coding. Or if you're an expert user and you're doing something crazy, something bespoke, you can write a completely custom Python script that does everything manually. You may not have a problem that looks anything like this. You may want to do something completely different. You may not even be analyzing an aircraft, but you want to use bits and pieces of Aviary and some of the helper functions that we have to set up a complex optimization problem. So you can manually set up your analyses components, put them in any order you want, set it up however you'd like, do whatever kind of crazy optimization you're trying to do. And we allow that too. And that's the beauty of an open source code, is you can dig through and just take the pieces that you want. So now that we have a better idea of kind of the capabilities of Aviary, I want to walk through a kind of pseudo example of what it would look like to actually set up and run a problem. We're going to start simple and work with that level 1 interface input file kind of interaction. So installing Aviary is pretty easy. It's available as a Python package you can install with pip. So it's a single line to install, and it comes with, and it'll work on all the dependencies and other packages you need. Basically, you don't need to worry about any of the installation setup details. We can take care of that for you. For our more advanced users, you can grab it directly off GitHub and do whatever you want with it. And once you have it installed, go through Aviary's documentation. We're proud of our documentation. We have a lot of information to help users get set up and hit the ground running using the code. So we have documentation on installation and walking through that. We have some overviews of the code and all the features and how to use them. We have some walkthroughs of example problems to help you practice on those before you try running your own aircraft. And we have a developer guide for if you want to contribute code. And All of this documentation is available online as well. And when you download Aviary, you can build it, have it locally on your machine as well. So we're trying to make it as easy to share as possible. So now that we've installed Aviary, we've read through the documentation, we're ready to actually build an aircraft. So this is an example of a simple text-based input file. It's basically all the parameters needed to define an aircraft, variable names, values, units. And it's pretty simple, pretty straightforward. It's a CSV, so you can edit it with a variety of different tools and software. We're working on a GUI to allow you to more visually interact with this file, setting it up, editing it, being able to look at a variable, read a description of it, better understand what it does before you add it to your model. That's something that's currently in development and will be coming soon. And you don't have to use this input file. You can define your aircraft using Python script too, and you jump in at a more complex level of the interface. But now we have an aircraft defined, so we have to design a mission for it to fly. And Aviary has a couple different ways to do that. My favorite is there is a great GUI to set it up visually and help you see kind of what you're asking the aircraft to do before you run that analysis. Or you can directly write up your mission programmatically using Python. The GUI is basically a shortcut where it'll write that script for you, so you don't have to know any coding in order to set up a mission. So now that we have our aircraft and we have the mission that we'd like to fly, we put those together and we actually execute an Aviary run. And as always, there are many ways that you can do this. Since we're working with an input file in this example, it would be as simple as this little one-liner, Aviary run input file name, and you're off to the races. If you're working with the more complex Python interfaces, then you have to actually start working with the code itself. For this example, we have our top level run function, and you provided the basic info, your input file, the mission information. You have a little bit more flexibility now that you're working with Python. You have more things you can define. Here we're setting a specific optimizer we want to use. Maybe we'd want to change settings on the optimizer, like maximum number of iterations or tolerances or things like that. We could also start adding in our external tools and subsystems here. And we're also can do things like overwrite where the output file goes. You start to get more capability as you go deeper into the code. And if you go too deep, you end up in what we call level 3, where it's a free-for-all, and you are just raw coding a Python script. And this is a lot more complex. You're actually manually setting up all of the connections between all of your analysis components. You're setting up your optimization problem. You're making sure that it executes correctly. You're doing everything manually. But this gives you the ultimate flexibility to set up your problem exactly how you want, and you have full control over the complete flow of information. And once you've run it, now you have to understand your results. It's not very helpful if you execute your analysis and you can't figure out what happened. So Aviary comes with a visual output called, we call it the dashboard, and that helps you understand, debug, and parse the results from your model with interactive reports. So we have things like a high-level summary of the finalized aircraft design after it's been optimized. You have detailed optimization reports if you really want to dig into lots of details like checking out your constraints or variable scaling or all sorts of detailed things like that. We have reports from each individual subsystem. If you're bringing in an external tool, you can also define a custom report that will get added automatically to this benchmark or this dashboard, excuse me. If you have any kind of visualizations or plots or tables or other pieces of information you think the user would like to know after they run the model. And we also have plots and figures of aircraft trajectories and time-dependent variables. So I'll show that next, but first I want to kind of show off the diagram on the left there. That's what's called an n-squared diagram. If you're not familiar, it's very similar to that chart I showed earlier showing the information flow of Aviary as a bunch of little squares. And we have all of these boxes are little individual pieces of discretized analysis. And this is an interactive report generated by OpenMDAO, and we just bake that into the dashboard. If you click on one of these boxes, it'll open up. It'll show you all the inputs and outputs for that analysis, and it shows you can trace where those inputs came from and where they go, which other components use that information downstream, which is a fantastic way to visualize how your model is laid out, figure out how information is being passed around, and it's also really useful for debugging if something unexpected happened. And this is another example of a more visually interesting report that Aviary generates, which is trajectory results. And this is showing the time history of every variable that changes with time, changes over the mission, color-coded by mission segment. It's cropped off here because it doesn't all fit in the slide, but you can keep scrolling and you get a whole lot of information, plots on everything. Here we have altitude and altitude rate shown, but things like velocity, acceleration, Mach number, drag, thrust, fuel flow, electric power consumption, all sorts of things like that. And you have the time history plots as those visually shown to you as well. And all of the information in this dashboard are files that exist and are created, and you can query those individually, look at the raw data, but we want to make sure we provide this more visual way to see this information because we find it's a lot faster to understand and parse if you can see what's going on in a mission profile, for example, rather than looking at a data table. But that still, of course, is an option if you'd like to do that. And finally, I'd like to discuss a little bit more detail about how you work with Aviary to add those external tools. If you have a tool you want to bring in, for example, if you have like a CFD code or something, you want to do some high fidelity aerodynamic analysis, how do I bring this in? So if you want to bring that tool in, or any tool really, you have to be able to communicate to Aviary what your system does and what to expect from it. Things like, are there new variables that you're adding to the problem? Are you adding any constraints? Are you adding design variables that the optimizer is allowed to play with? What parts of your analysis need to be run before the mission trajectory is solved? What happens during the mission analysis? Changes with time? Is there any post-processing you want to do after the mission is solved? That kind of thing. And to facilitate that, we have an API to handle that. And it's a Python object called the subsystem builder base, which is basically a template for a Python wrapper for your code. And this is a screenshot of that object. And basically, you fill in all the empty spots with what your code needs to do. So we have a function here called build pre-mission. And what it wants you to do is plop in an OpenMDAO system that contains the code that you would like to run before the mission. Hopefully relatively straightforward, and you keep going down that list. Are there any variables I need to add? Okay, I have a component that needs to run during the mission. You add all that in, and once it's in this format, Aviary can automatically handle putting it at the right spot in the model, running things as it needs to, adding the variables that you need, and then allows you to access them once the problem has been solved through the dashboard. So I want to end this presentation with some examples of how Aviary has been used within NASA and some examples of the aircraft that have been generated. Starting with this hangar of aircraft that was created by the AATT project. They wanted to create a series of conventional aircraft, your 737 or A320 equivalents, and use Aviary to model those with external subsystems wrapped in. For example, all of these images that you see here were generated using a NASA tool called OpenVSP to define all the geometry of the aircraft. And that also allows for those aircraft to be points of comparison or starting points to design more advanced configurations. So they've gone ahead and done the TTPW with Aviary and this kind of workflow, with the idea that we'll continue to create more advanced concepts using this kind of workflow and bringing in using these same tools, and slowly increase the complexity of models that they use. To dive a little bit deeper into that TCPW model, it's a non-proprietary version of that aircraft to allow us to share that model and openly publish its results. And that also allows us to more easily collaborate with other external partners that are interested in the concept or in our modeling techniques. And this particular aircraft model added in some external subsystems using geometry, aerodynamics, and propulsion. And they also made a EAP variant of it with a hybrid electric turbofans that would use electric power as a little boost during the climb phase. And all of that was made possible with Aviary. And this little plot on the right here is a radargram to kind of visualize the different subsystems that were included in that model, with the inner circle representing lower fidelity, the outer circle being higher fidelity, and then all of our different disciplines broken out. And almost all of these were either external tools that were wrapped and integrated into Aviary, or were supplementing Aviary's built-in analysis. In fact, of this model, the only piece that was not modified in any way was mission, and everything else was either replaced or supplemented with additional tools, methods, and calibration, things like that. So this is an example of a vehicle that Aviary can model out of the box without needing to bring in any additional tools or methods. You can download it and set up a model just like this. So this is a conceptual electrified freighter aircraft that we're working on as a partnership with EPFD. And it's a hybrid electric aircraft loosely based on the C-130. And what we've done is replace the outer pair of turboprops on the aircraft with all electric driven propellers. And legacy tools really struggle to model this kind of aircraft. You have multiple different kinds of propulsors on the aircraft that have unique fuel types, and you need to be able to decide how are you going to manage the split between power derived from fuel and power derived from your batteries and your electricity. What is that throttle split? But Aviary can do it out of the box. So we have calibrated the included weight and aerodynamic performance regressions that are the core methods of Aviary. We've calibrated those with publicly available data. And then for the engine models, we've set up a conventional turboshaft and an all-electric propeller. And the propeller modeling is done using the Hamilton standard method, which is included with the code. And we also share a simple motor and battery model with Aviary as well that you can use. So what that looks like in a little bit more detail is basically we have the concept of these little engine packages that give you the ability to model, and in this case, a propeller-based propulsor, but it gives you a little flexibility in how you define it. So in this engine over here, this is our this one would be all fuel. We have our little propeller-based engine package. And what we tell Aviary is for the propeller side of that, we would like to use the built-in Hamilton standard. And then for shaft power generation to power the propeller, we're going to use a turboshaft, and we're just going to provide it with a deck, engine deck, or a table of engine performance. And Aviary will figure out how to connect all of these pieces up, and it knows that all of these models bundled together is an engine. You don't treat these little pieces of analysis separately. It's an engine expected to output thrust, check if it has any fuel flow, and track that over the mission. And then to set up the electric engine, it's the same interface, but instead we're going to say, instead of using that turboshaft model, we're going to use the built-in motor model. And now Aviary knows to look for electric power, and if it sees electric power, it's going to hook that up to a battery model, and everything is handled for you. And you also don't have to use the Hamilton standard method. If you'd like any subsystem in Aviary, you can swap it out and put your own method in there as well. And if you do it through the interface, Aviary will know to bundle it up into a little propeller-powered propulsor and kind of take care of all those finicky connections of inputs and outputs for you. And this particular model we're working on, we're also doing some trades with things with the reserve mission, trying to see if it's an all-fuel reserve mission versus if electric power is allowed to be used in reserve, how that changes the design, sorts of interesting trades that can be done using Aviary as a framework. And to conclude the presentation, I want to leave you with a slide kind of talking about the impact that Aviary has had so far. So we open source released the code at the very end of the calendar year 2023. And since then, it's been used internally by NASA, by AATT, and we're partnering with EPFD to model more interesting aircraft concepts and prove and demonstrate the code and build up some trust in the tool and familiarity with the tool in the agency. But also, we've been doing a lot of partnerships externally. We have been partnering with government, other government agencies, industry, and academia. On the bottom there, I have a short list of some of our partners that the Aviary development team is directly collaborating with, and then we have other users that are using the tool more informally. Some of those partners are using Aviary as part of a contracted NRA, although they were not required to use Aviary. They chose to use Aviary to complete their tasks as a way to get familiarity with the tool, and because they see the vision that we see and want to work on testing out that more advanced digital design workflow and see how it works for them. And kind of the result of that is several design studies have been published using Aviary and kind of showing some of the unique features and capabilities that it has that the legacy tools could not. And we've gotten widespread interest pretty much across all spectrums of the aerospace industry. And that can be shown through the plot up there is our stars on GitHub, basically people favoriting the repository so they get notifications when things are updated there. And immediately after release, we got a ton of interest. And every single time that Aviary gets out in front of people, for example, calling out the little point there where we had a featured article on nasa.gov, immediately got a ton of interest. It's hard to tell looking through people's GitHub profiles who they are, but from what I can see, a lot of the time when we are publicly sharing Aviary, we're getting a lot of interest from students, which is really exciting to us. We really want to get our tool in front of everybody, not just for research or for product design, but also as a teaching and learning opportunity for students to learn about aircraft design, learn about the design process, and just develop good fundamental engineering skills. So we're very excited with that as well. And I want to give a huge shout out to the Aviary team. We've had a lot of people contributing a lot to this code and have done a tremendous job. Our current team members, former members who have contributed to the code at some point during its development, and all of our current and former advisors who come from across all of NASA's different aeronautics centers. So it's a very cross-program, cross-center project, and I'm very, very fortunate to be a part of such a wonderful team. And if you would like to try out Aviary, this is a QR code that I'm going to leave up, and you can scan it, and it will take you directly to our GitHub page, which has the documentation and instructions, and you can download a copy of the code. You can also just find us on GitHub under openmdao/Aviary, or install it through your Python package manager using that command there. So I encourage everyone to check it out, see how the tool works, and if you have any questions, comments, feedback, ways to improve the code, or if you want to make contributions yourself, you can reach out through, we have places on GitHub you can do that. You can directly reach out to the team using the email on the screen there, or you can find me looking up on NASA's directory, and feel free to send me an email. So thanks so much everyone for attending. I apologize for the little technical snafu halfway through, but thanks for sticking it out with me, and I'm happy to take any questions.
Thanks so much, Jason. That was fascinating and well worth the wait. So we've received a few questions, and I want to thank everyone who's submitted their questions so far, and encourage you to keep typing your questions into the chat, and we'll get to as many of them as we can in the time that we have today. And whatever questions we don't get to today, we will follow up with you afterwards via email with the answers to your questions. So let's see what we have here. Early on, Ed asked a question, what existing conceptual design tools are you contrasting Aviary with?
Yeah, so internally within NASA, we compare ourselves to the tools that we traditionally used that kind of made the backbone of Aviary, where we borrowed the methods and some of the capabilities from, which are FLOPS and GASP, which are available at differing levels of openness. Neither of them are open source. So those were our key points of comparison because we wanted to make sure that we were at least maintaining all the capabilities within NASA. We've also looked externally. There are other tools out there. Just off the top of my head, a couple ones that we've briefly looked at to varying, or some of them more in depth, some of them very brief. There's SWAV that's from Stanford. There's a couple of tools. There's Fast OAD and a couple more like that that are made by various places, universities, companies, or other government agencies or other countries that we've done some deep dives into, and some of them a more brief overview. So in the future, a more detailed comparison of results may be a good way forward. We haven't been able to go into that level of depth quite yet, but that's kind of what we're looking at.
Thank you. Looking in the chat, I'm not sure if this was just a comment, but I'm going to ask it as a question. Someone pointed out, nothing I've seen leads me to believe that it wouldn't be usable for modeling UAVs. Is that true?
Yeah, no, that's absolutely correct. I haven't really talked anything about UAVs or urban air mobility, VTOL or supersonics or things like that, not because Aviary can't model them, but just out of the box, we don't have methods to predict their performance that come with the tool. That could be something that's a future development effort, but right now, out of the box, Aviary only supports subsonic transports. But of course, if you have tools that can do the discipline analysis, you can wrap it, put it into Aviary, and all of a sudden Aviary is now capable of modeling that kind of aircraft.
Great, thank you. Okay, next question. What about capabilities for VTOL and analyzing vehicle trim? which can affect power requirement?
Yeah, so that's kind of related to the previous question, which is that that's not something that it does out of the box. But of course, once you add in the analysis needed to do that kind of analysis, that's the type of trade that Aviary is well set up to do. Problems that have interesting constraints or limitations that are important to the design, especially if you're doing any kind of optimization on that. So yeah, that's something that could be done with the tool. And in the future, I really hope that someone who's an expert in that space could pick it up and do those kinds of designs.
Lots of possibilities there. Thank you. Okay, here's another one. The level 3 interface to Aviary seems to still abstract the traditional OpenMDAO interface away. Is it straightforward to manually construct an OpenMDAO model using the groups and components in Aviary?
Absolutely, yeah. So that screenshot of code that I showed is just one piece of this. So that was a model we set up that was custom building. It was just a 737 model, but that was hundreds of lines of code. Some of them were using helper functions in Aviary, but sometimes we were directly interfacing with the OpenMDAO interface. That was, I guess I would say, a light use of level 3, where we weren't doing everything from scratch. But since yeah, every single piece of analysis in Aviary is in OpenMDAO components and groups, so you can absolutely take those out and use them individually or manually set them up. If you just want to do a little tiny example problem that just has a couple of those subsystems, or if you just want to take those, you don't even want to use them in Aviary, you just want that analysis method for something completely unrelated, absolutely go in there and dig it out.
That's great. Thank you. Okay, here's another one. Is there an interface to work with MATLAB Simulink models for some of these components?
We haven't actually done any tests or tried out using any interactions with MATLAB directly. That will be a little bit more complicated because right now everything is assumed to use the Python interface. So there isn't a direct communication with other programming languages. So that's currently a limitation of the tool, is it doesn't have a way of doing that kind of direct communication. Now, if you were able to wrap your MATLAB script or give it a Python interface that Aviary could communicate with, then you could use it. You're kind of losing some of the capabilities of MATLAB in that respect, possibly. So that's kind of an area of possible future development, not something that is well supported at this moment.
Okay. And this next question sounds very similar. This person's asking, could Aviary work as an executive interface with another tool like Charms for rotorcraft modeling? And it sounds like you may have already answered that as well.
I think partially for a tool that's more of a comprehensive, it can kind of do the whole design loop on its own. That's not actually something we've tried to bring into Aviary, but theoretically, it's definitely possible. All you would have to do is maybe write something a little more custom to wrap that tool in a way that you could pass the inputs in Aviary style, and then the outputs are presented in a way that you could possibly use or leverage Aviary's dashboard and all the interactivity. That's something that could be possible. It would take a little bit more legwork. That's a really interesting application that we haven't really considered too much. That's a great idea.
Excellent. Thank you. Okay, how about this one? Is it a good tool for system identification?
So systems identification is something I'm only vaguely familiar with and don't have a lot of experience with. So I don't feel comfortable making a definitive answer if this would be particularly good for your application, but feel free to reach out to the Aviary team, and there are definitely people on the team that can maybe better answer that question. Apologies.
Sounds good. Okay, here's another one. Are you aware of any Aviary early adopters focused on MDAO in hypersonics?
Oh, so yeah, hypersonics. Currently, we don't have a lot of direct interactions with the hypersonics team. I've informally talked with them a couple times. Here at Langley, the hypersonics team has some unique applications that they're trying to pursue that are related to but aren't part of Aviary's core competencies. So we're trying to discuss if there's a way to either merge the tools or make our tools compatible. So that's something that is only very tentatively being explored. On its own, of course, Aviary could model hypersonics just by slotting in the right subsystems and the right analysis. The hypersonics, because it is so specialized, sometimes they prefer to use their own tools. Sometimes they don't mind using something like Aviary. It's an open discussion, I guess, is what I'll leave it at.
Understood. Thanks for that one. And how about this one? Great project. Thanks for the presentation. Could Aviary be used for aerodynamic design studies of ground vehicle bodies?
That's good. That's definitely a really exciting application that's not aircraft based. In this case, that would be something that you would need to do a little bit more customization because Aviary has some basic assumptions about that it is an aircraft. For example, all of the variable names are all pieces of aircraft. You have variables about wings and about fuselages. So you basically have to ignore a lot of those and set up analysis components that are specific to ground vehicles. But the design process of it's on its own, sizing a vehicle, doing some sort of mission or some sort of application of it, and iterating upon that, that's just a fundamental part of design. So Aviary's framework could still be very useful to set that up, especially if a very large and complex OpenMDAO problem is something that don't have a lot of experience working with. Aviary is at the very least a fantastic example to look at and see how you can replicate it. Or maybe you could try sliding in all those different analysis components, and theoretically that would work. It's just something outside of what we were initially expecting it to be used for. But we're really excited to hear questions like that of how people can use the code outside of the little domain of aircraft design.
Interesting. Yes. Okay, here is another question. We have time for a few more. And like I said, keep typing them into the chat, and whatever we don't get to in our time today, we will respond to you via email afterward. So here's a question. How does the user specify the power flow architecture, i.e. the connectivity between components and power paths in, say, a hybrid electric architecture? Is this done graphically through GUI?
So currently we don't have any GUI for that. That's something that so I have a personal interest in modeling those kinds of vehicles, and that's something that I feel like might be the easiest way to do that. Currently, you would have to do it by defining your propulsion subsystem with a series of OpenMDAO components that are connected together in the way that you'd like, and you hand that collective group to Aviary and say, this is my propulsion system and this is how it behaves. Use this, slot it in. So currently it's pretty rudimentary if you don't do some of those connections yourselves. For example, if you have a bunch of different engines that use electric power, Aviary is just going to hook them all up to some sort of sink that accepts electric power as an input, like a battery, and the battery is getting a request for how much power to get. It'll just assume that connection. It won't understand if you want to do a split. Oh, I have 3 different kinds of batteries that want to be used different ways. That's not something that it'll understand out of the box. You'll need to do a little bit more tinkering to custom set up a power flow.
Okay, very good. Thank you. And then we have, does Aviary handle space planes, or at least gliders, to model space planes on descent and landing?
Another application that's currently outside of what we've tried so far, we have a lot of places we'd like Aviary to go, but we're still pretty young as a project. We've been released for less than a year, so we haven't gotten to the really weird stuff. Space planes would be fantastically interesting. We've talked about ways to handle at the very least different atmospheres. For example, flying on other planets. Space planes would be an extension of that kind of capability of going into orbit. That would be a really awesome thing that would kind of bring aeronautics and space together. So future goals.
Possibilities are endless, right? Here's another one. You mentioned earlier that there were some models that were designed in OpenVSP. Were these models geometries defined and then moved to Aviary for analysis? What was the benefit in moving these models to Aviary as opposed to running tests using VSP Aero in OpenVSP? And could models be created from scratch in Aviary as well?
Yeah, great question. So the workflow that AATT used for this aircraft is they used both VSP and VSP Aero. and they used VSP as a way to define the geometry for the TTBW and kind of parametrically as they vary things, getting more accurate estimates for surface area and things like that as they change like wing corridor, things like that. So that's how they hooked it into the model. There's a wrapper for that team has. It's currently internal to NASA. We're talking about publishing that more openly. So that's what was done on the geometry side and why they chose to use that. The built-in geometry regressions that come with Aviary assume a conventional cantilever wing, so they weren't quite accurate for TTW. And then on the aerodynamics side, they actually chose to take the geometry of the aircraft, run it through VSP Aero, and generate a drag polar. They just ran a series of cases, generated a drag polar, and then gave that to Aviary for mission analysis, where it would just interpolate on that table to save on some computation time of not running it hundreds or thousands of times for every single point along the mission trajectory, every single iteration. You could also put it in the loop, of course. That's kind of how they used VSP Aero in that application.
Excellent. Thank you, Jason. I think I have time for one or two more. We do have a bunch more questions. Whatever we don't get to, we'll respond via email. Apologies if you've already covered this, but can Aviary model turbines as well?
So Aviary has the capability of doing like cycle design if you bring in an external tool. For example, the TTPW model, we had a PyCycle model doing cycle design. We also, the ATT group has a wrapper for rudimentary wrapper for MPSS. MPSS is so freeform that you can't have a one-size-fits-all wrapper, but they have a fairly genericized one too. So you can use that to do turbine design within Aviary, and you can do your cycle design as part of the overall aircraft optimization.
Great. Okay, then I think we'll do one final question, and then we'll get back to any remaining questions via email. You mentioned Aviary is built on Dymos as well. Have you looked at dynamic transient problems with Aviary? Does Aviary support these? Also, are there avenues for co-design?
Yeah, so transient analysis is something that we're aware of and are interested in. That's something that will be kind of like a next evolution, next step to look into. So it's a space that we have our eye on, but haven't done any examples with that yet. Maybe I don't quite fully understand what you're asking for co-design. If you could follow up, you send me an email, or I'd be happy to figure that out for you. I don't fully understand the question. Apologies.
No, that sounds great. And that's about all the time we have for questions today. Thank you so much, Jason. As we wrap up, I just want to mention a quick overview about NASA software. NASA software is a free resource and is available through NASA software catalog, which can be accessed directly at software.nasa.gov or through the agency technology portal at technology.nasa.gov. And I understand that that Aviary will be added to this catalog and will be available on our website within the next day or two. NASA software ranges from open source codes to more restricted downloadable codes. And the software categories that you see here include a high-level summary of the types of codes found in that category to assist you in your search. And that's about all the time we have for today. Very interesting presentation. Thank you very much. And again, if we didn't get to your question, we'll follow up with you by email within the next week. And if you still have an additional question, please feel free to email them to, if you caught that address on the screen, maybe he can put that back. And we'll follow up with some answers to those questions. And we really appreciate the interest. And we appreciate your presentation today, Jason. Thank you so much.
Thank you everyone for attending and for the really fantastic questions. I love getting interesting ideas for new applications to the tools. It's very exciting.
Absolutely. Very engaging today. Thank you so much. Have a great day, everyone.